Hi, so now I'm going to talk about moment around about an object, about a pivot. Well, it's not going to be about an object, it's about a pivot or a point. Okay, so it's like we have the seesaw here, right? So you have hold on, I always have to choose these things, it's hard. Okay, yeah. Okay, so we have this point here, okay, and there's going to be a moment about this point. So you got a mass in here, and you have a mass in here. I don't know why this is happening. Anyway, this is really weird. Hold on, guys. I'm just trying to understand something here. Okay. So you see, the little kid's like 2 meters away, right? From the point, and he weighs, well, he doesn't weigh, he masses 30 kilograms because force equals mass times acceleration. The mass is going to be 30 kilograms, but the force is going to be the mass times some kind of acceleration. In this case, it's going to be equal to his weight, which equals mass times the acceleration of gravity, which is 30 times approximately 9.81 meters per second squared. But let's just say it's, okay, 9.81, fine, let's just leave it that. Yeah, let's just leave it at that. So this is going to be his weight, okay? Now, we're not worried about the weight now, not the force, just the mass. So you have the mass, which is 30, okay, around 2 meters. So you put 2 meters in here. There you go. So it's just going to be 60. But then you have something else. This will be like the right moment. Okay, why? Because it's rotating this stuff. Let me choose another one here now. It's rotating this thing clockwise. Okay, if you see like this arrow in here is clockwise, and like that is counterclockwise. So we're gonna call this the positive moment. All right, and I'm gonna consider this point P here 0. All right, so we have 30 times 2 minus, because now you have a negative 2 meters, all right, negative 2 times 20. So in the end, you have 60 minus 40, which equals 20. So what's going to be the 20? It's called what we call the moment about an object, or about a point, about a pivot. Okay, we could say that's the moment about P, like that, maybe, right? So the book calls it right moment, left moment, but it doesn't really matter. Anyway, for example, I'm going to show you another picture here, which is pretty much self-explanatory. I'm going to make it big. So, see here, you have a point here, we're just going to call O or 0, whatever. And then you have an x1, which is this distance with a mass 1. You have an x2, which is this distance with a mass 2. x3, which is this distance. So you're going to add them all together, and this is going to be a moment about this O thing, or 0 thing. Okay? If they're all 0, the system is in equilibrium. That means that the same... it's weird now, but the same force that's going to go down, pretend that this is a seesaw, okay? Here is the same force that's going to go down here. So the seesaw will not go this way or this way. It's just going to stand in horizontal, okay? It'll just remain horizontal. But there's a difference. You see, right now we're not talking about the force. We're just talking about the mass. So the moment about this point is just going to be the summation of all the masses times the distances, right? For example, you have the mass 1, which is x1. You have the mass 2, which is x2 from this point. You have mass 3, which is x3 from this point. So this is just going to be called the center of mass, okay? Well, not yet. I'm getting ahead of myself, but when we do some kind of calculation, this whole thing is just going to be called the center of mass. Now you also have the center of gravity. The center of gravity is when you apply the force. Because you see, right now, in here, you have this mass 3, which is a distance x3 from the moment, from the point O here, okay, of this seesaw. But there's no force in here. For example, there could be a force this way, There could be a force this way, there could be a force this way. Right now there's no force, it's just a mass. So with all this stuff in here, okay, when we do this and we divide it by the total mass, and I'm going to show you this later, we're going to find the center of mass. Now, the center of mass is the same center of gravity when the gravity is homogeneous everywhere. So let's just say that the same gravity that you go here is the same one that you go here, same one here, the same one here. It's the same one everywhere. Then the center of mass is going to be equal to the center of gravity. Now, let's just say that for some weird, whatever situation, you have a gravity here that's way larger and it's in a different, for example, for this point here, the gravity is like this. It's huge and it's in this direction. Then the center of mass is going to be different from the center of gravity. But for this physics, for, everyday situations here on Earth, okay, on a planet, you're going to find that the center of mass is the same as the center of gravity. Let's just keep going now. Okay, let me see if this works in here. I don't know why the icons here are just changing. I don't know why. Okay, so you see the summation, right? This summation in here, this is going to be equal to what? This thing is going to be equal to the summation, all right, from I is equal to 1. Okay, I chose something else. All the way to n, yeah, of. Well, you're gonna have a mass I, okay, times xi minus x. Well, I'm gonna call the x average. This x average is actually the center of mass. Okay, we're not talking about the center of gravity right now because there's no force. It's just the center of mass. So this is going to be equal to the summation I is equal to 1 all the way to n of mi xi. What is this xi minus x? Well, let's just say that the x, I just want to show you something else. This x bar is going to be right here. Okay, we're going to consider this the pivot. So this x bar is going to be right here. So if xi is positive, like 2 meters, then it'll be around here. Xi is going to be here, and it'll be 2 meters, okay, 2 meters away. If fxi is negative, like 3 meters negative, kind of like here, all right, so there's going to be a space in here of 3 meters, but it'll be negative because it'll be, hold on, actually, I don't know why the book is doing it like that. Yeah, it's kind of weird, right? Because if it's going to be 3 meters, then it was supposed to be like, let's just say that this is 0, okay? So xi minus, yeah, it was supposed to be x bar minus xi, okay? Yeah, it's kind of like the book is considering this positive and this to be negative. I don't know why it does this, but let's just go with it. Because you see, when xi minus x bar, right? Well, let's just say that x bar is right here and it's 0. So when this thing here, yeah, that's really creepy, man. That's really creepy. Or maybe not. Oh yeah, no, hold on. It's right. This is positive and this is negative, okay? So you do xi minus x bar. Well, x bar is just going to be 0, right? Because we're just pretending that it's 0 for now to make things simple. So if xi is 2 meters, it's going to be 2 minus 0, which is 2. When it's 3 meters over here to the left, xi is going to be minus 3 minus 0, which is minus 3. So yeah, it's right. Okay, so coming back here to this equation here that I'm doing, now we're going to have minus, okay, and we want something to be in equilibrium. So it'll be minus the summation of I is equal to all the way to n, okay, of mi times x bar. Okay, and I want this the system to be in equilibrium, whatever. I want the system to be balanced, so there's no the seesaw in here is not going to go like this or like that. It's not going to rotate about this point pivot here. It will just remain stationary horizontally. So I'm going to pass this thing over here, and it'll be this summation here. I'm just going to copy and paste because it's faster. It'll be this summation, okay, and I'm going to erase this thing here. It'll be equal to this summation here. I'm just going to put an equal sign, all right? So that means that this thing right here, the balanced x, or the pivot, whatever you want to call it, is going to be equal to what? It'll be equal to this thing. Oh, here's what I can do. Make it even simpler. I can just get this thing and divide it over here. Okay? It'll be divided like this. Now, here's the thing. What is this thing over here? The summation of all the masses times the distance from the pivot. This is going to be the moment about the pivot. See right here, the m0? So this is going to be equal to the moment about the object divided by the whole mass. I don't know if you call it the total mass like this. It could be like, oh man, total mass, whatever. Because it's the first mass plus the second mass plus the third mass plus, so, all right? So you have that. Now, there's something else too that we can do. Let's just say that you want to apply force now to talk about the center of gravity, because this will be the center of mass, okay? Now, let's just say that we want to talk about the center of gravity. So for each one, it's going to be the same gravity, okay? The gravity is not changing. The same gravity is going to be applied to every point of that seesaw. So what you're going to have is, well, let me just explain this a little bit differently. Okay, hold on. Maybe there's something else in here. Because you see, okay, when you have this stuff, okay? Now let's just say that you have a force, a total force being applied to a seesaw. So what are you gonna have? You're gonna have m1 times a plus m2 times a plus, right? And you keep going, mn times a. So this is going to be the total force. So what is that? Okay, the force equals the entire mass, I'm going to say this mass total, times the acceleration. Okay, now if we're applying force now you got a torque. What is a torque? Is the power of a mass to cause a rotation about a certain point. Let's just say that you're applying a force right here. Is there going to be rotation? No, because you're applying the force right at the pivot. Okay, now if you apply a force in here and you don't apply any other force in here, you're just applying the force in here, what's going to happen to the seesaw? It'll be like this, right? It'll rotate clockwise. So it caused a torque. It caused the rotation about this point here. Okay, now what is the power of the rotation? The power of the rotation is going to be, for example, for this mass 3, is going to be the mass 3, okay, times its distance from the pivot, which is going to be x3, times the force in this case, which is the times the acceleration. Okay, this is going to be the torque. So you see that the torque equals the force, because you have mass times acceleration, so you have the force 3 times x3. That's torque, okay? Because what's the difference between torque and force? Force is just some kind of force that you're applying, mass times acceleration at a point. The torque is the possibility that this force has to make a rotation of the seesaw about that point. For example, if you make, like I said, if you apply a force right here, what is it going to be? Here it's x0, okay? So the force 0 is going to be the mass at 0, right, times the acceleration of this force times x0. But what is x0 to x0? It's 0. So, well, this is the torque. I'm sorry, this is the torque. Torque at 0. It's the mass at 0 times the acceleration at 0, which is the force at 0 times x0. Now, x0 to 0 is just 0, because x0 is the pivot. So when you apply a force on the pivot, whatever is around the pivot is not going to rotate. All right? So what am I trying to say with this? Is that if you apply, for example, an acceleration here, if you put an acceleration here, then you're multiplying an acceleration here and you're multiplying an acceleration here. All right? There's going to be an acceleration here and an acceleration here. Now look at this. What is this stuff? Now we're talking about something else, okay? Okay, I'm just going to keep going. So this stuff was equal to this without the acceleration, but I put the acceleration. So I'm going to put the acceleration here and I'm going to put the acceleration here. Now, what is this equal to? The moment about the origin times the acceleration is going to be the torque about the origin divided by all the masses times the acceleration, which equals to what? The entire force. Okay? So the moment, considering that, man, this is supposed to be like that. Hold on. This is really weird. Yeah. Crazy. Okay. So the center of mass is going to be equal to the entire moment about an object divided by the total mass. Okay, let's put total mass, which is the same as the center of gravity. So this is the center of mass equals the total mass about the point O, whatever you want to call it, divided by the total mass everywhere, which equals, right, the torque about the same point divided by the total force everywhere. This video is just to show you this, okay? Now, I know this seems boring to listen to me talking about this stuff, but for people that don't understand, if you already know what I'm talking about, you go like, okay, this is obvious. Why is this guy making this 20-minute, 30-minute, 40-minute video just to talk about this thing? But this video is for people that have never seen this before. So that's why I do this. Now we're gonna go da-da-da-da. Okay. All right. The moment about the origin. Just want to see something here. Find the center of mass of the linear system shown in this figure. So this is the figure, all right? Gotta do it like that. So you see that the 0 is over here, all right? Now what are we gonna do? Well, the center of mass, remember, it was gonna be the sum of all the moment about this stuff, the sum of all the masses times their distances from the 0 point divided by the entire mass. Okay, that's the center of mass. So x bar is just going to be, well, let's do it 10 minus 5, 10 times minus 5, right? This one here, which is going to be minus 50, plus you have 15 times 0. So it's 0 plus 5 times 4, which is 20, plus 10 times 7, which is 70, right? So here you have 90 divided by, well, you got to divide this whole thing by the sum of all the masses. So you have 10 plus 15, 25, plus 5, 30, plus 10, 40, all right? So let's do this. This is going to be minus 30 plus 70, 40 divided by 41. So this is going to be the center of mass, okay? which is the same thing as the moment about this origin divided by the sum of the total mass. So you have 1. So what does this mean? That means that you got a center of the center of mass, guys, is actually at 1. Okay, the center of mass. I'll show you what it means. If you make the pivot becomes here, all right, I'm gonna make the pivot be right here. The seesaw is gonna weigh. Yes, then of course you gotta apply a force, because as long as you have mass in distance from the pivot, but you don't have any force, nothing's gonna happen, right? Now let's just say that you're gonna apply a force of gravity everywhere. It's the same force of gravity all over this thing, right? At this point here, the seesaw is going to go like this. You have a rotation of 1, okay, the torque is going to be 1 clockwise. Now, if the center of mass is 1, that means that if you move the pivot from this point to this point right here, then the seesaw is not going to move. Even if you apply all the forces, the seesaw is going to remain horizontal, okay? Because this is the center of mass, and because the gravity is the same everywhere here, this is also the center of gravity. Guys, that'll be it for this video.